Imagine sitting inside a commercial jetliner, cruising smoothly at 30,000 feet while sipping a hot cup of coffee. You feel completely safe. But right outside your window, inside the jet engine, pieces of metal are spinning at over 10,000 rotations per minute while being blasted by gases reaching 1,600 degrees Celsius. That is hotter than the melting point of the metal itself. Yet they do not melt. In fact, if just one of these components fails for a single millisecond, the entire engine disintegrates instantly. These are turbine blades, the most complex, highly engineered, and terrifyingly resilient objects ever created by mankind. Most people never think about this, but the story of how they are built will completely change how you look at a simple airplane ride forever. Think about this. A modern jet turbine blade handles centrifugal forces equivalent to the weight of a double-decker bus hanging off its tip. If it deforms by even the thickness of human hair, it will scrape the outer engine casing and cause a catastrophic, explosive failure. Engineers spend decades trying to solve this problem, failing over and over again as standard metal shattered under pressure. But here's what nobody tells you. The secret to conquering this extreme environment wasn't found in a futuristic tech lab, but deep inside the literal crust of the Earth, buried thousands of miles away. What happens next surprised even experienced engineers. Because to survive the fires of a jet engine, you first have to harvest raw elements from the most brutal mines on the planet. Our journey begins in the remote, sun-scorched earth of Western Australia and the deep underground mines of South Africa. Here, miners extract raw nickel, rhenium, and ruthenium, exotic elements that form the backbone of what scientists call single-crystal superalloys. These aren't your everyday metals. Rhenium is so rare that global annual production is less than 60 tons, yet costs over $3,000 per kilogram. We haul thousands of tons of raw or across vast oceans to high-tech refining facilities in Europe and North America, burning massive amounts of fuel just to isolate a handful of precious, ultra-pure material. The environmental footprint of extracting just 1 kilogram of these superalloys is staggering, requiring massive energy grids to purify the metals to a mind-boggling 99.99% purity level. But this extreme purity is non-negotiable, because a single atom of contamination from a cheap metal like iron can ruin the entire batch. Once refined, these raw elements are shipped to advanced smelting facilities, where they are blended together inside sealed vacuum induction furnaces to prevent any contact with oxygen. The resulting superalloy ingots are heavy, dense, and brutally expensive, costing more than a luxury sports car per shipment. Workers operating massive overhead cranes wear specialized silver heat-reflective suits, moving through air that smells faintly of ozone and burning electricity. These ingots are perfectly uniform, but right now, they are just solid blocks of lifeless metal. To transform them into aerodynamic masterpieces capable of defying physics, we have to use an ancient sculpting technique infused with terrifying modern technology. And this is where it gets truly extraordinary, because the shape of the blade is created using something that melts at the touch of a human finger. The manufacturing process does not begin with metal. It begins with wax. In a pristine, temperature-controlled clean room running at exactly 22 degrees Celsius, automated injection molding machines pump liquid industrial wax into precision steel dies at a pressure of 80 bar. Within seconds, a perfect, blue wax replica of the turbine blade emerges. Human operators gently lift these delicate wax shapes and assemble them onto a central wax column, creating a structure known as a casting tree that looks like a strange, futuristic mechanical plant. Every single wax blade must be flawless, because any scratch or speck of dust on the wax will be permanently copied into the final metal blade. But these fragile wax trees are about to face a brutal transformation, immersed in a liquid substance that turns them harder than rock. We take this wax tree and repeatedly dip it into a thick, milky slurry of liquid ceramic zircon and silica. Robotic arms move with eerie precision, lifting the dripping tree and dusting it with fine ceramic sand grains in a fluidized bed, repeating this process up to 10 times over 48 hours. As the layers dry, they form a thick, rock-hard ceramic shell around the wax. Once the shell is fully cured, it is placed into a high-pressure steam autoclave running at 170 degrees Celsius and 10 bar pressure. In a sudden, violent burst of heat, the wax inside melts instantly and drains out the bottom, leaving behind a perfectly hollow ceramic mold. The air fills with a sweet, heavy smell of melted wax as it pools in recycling vats, leaving behind an empty ceramic ghost of our turbine blade that is ready to meet the fire. Now, the real magic happens inside a massive vacuum casting furnace. The hollow ceramic molds are preheated to an astonishing 1,500 degrees Celsius to prevent the molten metal from shattering them upon contact. Simultaneously, the nickel superalloy ingot is melted via induction currents at exactly 1,550 degrees Celsius, transforming into a blindingly bright, white-hot liquid. A mechanical arm pours this liquid metal into the top of the hollow ceramic mold under a total vacuum to eliminate even a single bubble of air. The liquid metal fills every tiny crevice of the blade's internal cooling passages at a speed of 2 liters per second. But if we let this metal cool normally, it will form millions of microscopic crystal grains, creating tiny boundary lines where the blade will easily crack and snap under pressure. To prevent this, we must perform a casting trick that defies the laws of nature. This is the pinnacle of metallurgy, single crystal casting. The filled ceramic mold is slowly withdrawn downward out of the heating zone into a cooled liquid metal bath at a painfully slow rate of just 5 millimeters per minute. At the base of the mold lies a tiny, corkscrew-shaped passage called a pigtail selector. As the metal cools from the bottom up, multiple metal crystals begin to grow, but as they navigate the tight, spiraling corkscrew, only one single crystal grain manages to squeeze through to the top. This single crystal then grows smoothly throughout the entire body of the turbine blade. When it finishes cooling after several grueling hours, the entire turbine blade is made of just one solitary, continuous crystal molecule with absolutely no internal grain boundaries. What happens next surprised even experienced engineers, because extracting this metallic masterpiece requires a display of sheer, unadulterated violence. To free the metal blade, the rock-hard ceramic mold must be completely destroyed. Knockout machines violently shake and hammer the assembly with pneumatic pistons, shattering the outer shell into thousands of white ceramic shards in a deafening roar of metal against stone. The air fills with thick, powdery white dust as high-pressure water blasting booths strip away the stubborn ceramic remnants stuck inside the internal cooling channels. What emerges from the dust is a rough, dull gray metallic tree of turbine blades. Industrial bandsaws spinning at 3,000 RPM slice the individual blades away from the central pouring column, casting off bright showers of yellow sparks. The raw blades are finally free, but they look nothing like the shiny components you see in pictures. They are rough, discolored, and completely unready for flight. Now, the metal must undergo extreme heat treatment to lock its molecular structure into place. For 24 continuous hours, the blades are baked inside a specialized vacuum furnace at 1,300 degrees Celsius, then rapidly cooled or quenched in a blast of pressurized argon gas. This thermal roller coaster reorganizes the atoms, making the superalloy incredibly tough. Next, the blades are moved to advanced computer-controlled EDM or electrical discharge machining centers. Instead of using a traditional metal drill, which would instantly break against the superalloy, these machines use a brass wire charged with high-voltage electricity. Submerged in a bath of deionized water, the electric arc vaporizes a tough metal at a microscopic level, cutting complex rude geometries and drilling hundreds of tiny, angled cooling holes through the walls of the blade. The smell of vaporized metal and electrical ozone fills the air as the machine hums with a high-pitched, steady buzz. These tiny cooling holes are an engineering miracle. When the engine is running, relatively cool air from the compressor is pumped to the hollow inside of the blade and bleeds out of these hundreds of tiny holes, creating a thin, protective blanket of cool air over the outer surface. This prevents the roaring 1,600-degree exhaust gases from ever touching the actual metal. To give the blade its final line of defense, it enters a state-of-the-art electron beam physical vapor deposition chamber. Inside this high-vacuum machine, a powerful laser blasts a puck of ceramic material, turning it into a glowing cloud of vapor. The turbine blades are spun through this cloud, allowing a microscopic, 7-layer thermal barrier coating of yttria-stabilized zirconia to settle onto the surface. This ceramic coating is an incredible insulator, ensuring the metal stays cool enough to prevent the engine from destroying itself in midair. In this ultra-modern facility, Humans don't do the heavy lifting. Highly articulated six-axis robotic arms slide silently along floor tracks, transferring blades between stations with perfect consistency. Automated optical scanners equipped with blue laser AI vision sweep across every square millimeter of the finished blades, comparing the physical object to a digital twin model. If a blade deviates from the blueprint by even 5 microns, less than a fraction of a single red blood cell, the system flags it instantly. The global aviation industry tolerates a rejection rate of absolutely 0% for these components, meaning any defect results in the immediate destruction of a $40,000 blade. But as advanced as these machines are, they are completely blind to certain hidden dangers, which is why the ultimate test of survival relies on an unexpected combination of chemistry and human intuition. To catch invisible cracks beneath the surface, the blades undergo a fluorescent penetrant inspection. They are dipped into a bright neon green chemical dye that creeps into the microscopic fractures, washed clean, and placed under an intense ultraviolet blacklight. A highly trained human inspector, wearing specialized dark-filtered glasses, peers through a magnifying lens in a pitch-black room. If a blade has even a microscopic stress fracture, it glows like a neon sign under the UV light. While machines can scan dimensions, only the seasoned eye of a master inspector can interpret the subtle shifts in the dye's glow. Following this, sample blades from each batch are subjected to brutal non-destructive testing, including high-energy X-ray imaging and ultrasound scans that peer deep inside the solid crystal structure to look for microscopic air pockets. The final gauntlet is a terrifying stress test designed to replicate the absolute worst-case scenario in flight. Individual blades are clamped into a massive spin rig chamber that pumps the atmosphere out to create a vacuum, then spins the blade up to an incredible 15,000 RPM while blasting it with high-intensity infrared heaters. Engineers sit behind thick blast-resistant glass windows, monitoring real-time data feeds from hundreds of sensors tracking vibration, thermal expansion, and resonance. The machine lets out a deep, terrifying rumble that vibrates through the concrete floor of the facility. If a blade passes this test without stretching or cracking by even a fraction of a millimeter, it receives its International Aviation Certification stamp. This stamp is its passport to the skies, proving it is ready to be bolted into an engine that will carry hundreds of human lives across the globe. When you look at the big picture, the global scale of this industry is truly staggering. Every single year, manufacturing facilities around the world produce over 40 million turbine blades to keep global aviation and power generation networks running. The total global market value for these components alone exceeds $35 billion annually, driven by a highly specialized workforce of over 200,000 engineers, metallurgists, and technicians worldwide. The production landscape is dominated by an elite group of countries, with the United States leading at 35% of global output, followed closely by the United Kingdom at 20%, Germany at 15%, France at 10%, and Japan holding a crucial 10% share. To put that in perspective, the value of the turbine blades inside a single wide-body jet engine is worth more than the entire value of an entire regional airport terminal built 50 years ago. 50 years ago, turbine blades were forged from simple iron-nickel mixtures and could barely last a few hundred hours before warping into useless junk. Today, because of single crystal technology and advanced ceramic coatings, these components can fly for over 25,000 hours straight without a single maintenance check. Over the next 10 years, the industry is projected to undergo an even more radical transformation, shifting toward 3D printed ceramic matrices and AI-designed blade shapes that can handle temperatures up to 1,800 degrees Celsius, drastically reducing carbon emissions. Did you know that a single turbine blade extracts more horsepower from a jet engine's gas stream than an entire grid of Formula One racing cars combined? Or that the centrifugal force pulling on that blade is so high that if it detached, it would blast through 3 inches of armored steel casing like a bullet? It is an object that pushes the absolute boundaries of what physical matter can endure. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, Tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.